Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the first module of this course, that is the introduction module. And the idea behind this module is to give you a basic introduction to operating systems. So within the first module, currently we are on the second topic, that is introduction to operating system. So here through a series of videos, we are trying to understand what is an operating system and what does it do. So as we already know, the operating system is a special piece of software that is responsible for managing the computer hardware. And there are several hardware components, right? In the computer, there is the CPU, then we have the memory, and then we have a set of IO devices. So we have been looking individually at each of these hardware components and seeing how the operating system manages them. So now in this video, I want to talk about a specific class of IO devices, that is the storage devices. These devices are used by the computer applications to store their data persistently, and the operating system does a whole bunch of things to manage them and make it easy and efficient to use these storage devices. So let us see what all the operating system does in the context of storage devices. So let's get started. So let us start the discussion by understanding or recalling why do we need the storage devices. So as you can see, this is the memory hierarchy that we saw in the video where we studied about the computer memory, right? So the memory hierarchy has several layers, and this is the primary memory, then we have the secondary memory, and then there is the tertiary memory. So the primary memory, that is the main memory system of the computer, that is constituted by registers, cache, and the main memory. The problem with the primary memory is that it is volatile in nature and it depends on electricity. So when the electric supply or the power supply is not there, then the contents of the memory will be lost. So we cannot rely on the primary memory to store our data for a long period of time, because every time the system shuts down, all the data is lost. So that is why we have the secondary memory, and here we have a bunch of storage devices which are persistent in nature. So what does it mean to be persistent? Basically, whatever data that you store here will remain on the storage device even if the power supply is not there. They rely on different types of technologies that does not depend on the electricity. So they are able to store data for a long periods of time. And all the data that we care about, this is the place where the users store their data, right? So now we understand why do we need the storage devices, that is to store our data for a long periods of time. So here on this slide, we have different examples of storage devices that are persistent in nature. So the first example is the solid state disk or the SSD. So these devices are based on flash based semiconductor technology, and they are also known as non-volatile memory. And if you compare this with the other forms of storage devices, that is the hard disk, the CD, DVD, or the pen drives, then they have a much more higher speed and they are also much more stable. And that is why this non-volatile memory or the SSD has been becoming the more preferred choice for persistent storage device in the computer system. Then after SSD, we have the hard disk drive. So the hard disk drive has been the most popular choice of persistent storage device in the computer system for a very long time. And as you can see, it's a mechanical device. So there are several moving parts in the hard disk. There is this disk motor on which the disk platters have been mounted. So that motor rotates these disk platters and the data is stored on these platters, which is read by this disk arm. So the disk arm moves over these platters and reads the data. So as you can see, since there are several moving parts, so this is a mechanical device. And then we have some examples of storage devices which are persistent as well as portable in nature. So you can carry these devices, that is the pen drive and the CD-ROM. So the CD or the DVD are somewhat older forms of technology. They are based on optical light. So they use light to read or write data, right? And slowly they have been losing their popularity in favor of the more recent and more compact, that is the pen drive. So as you can see, the pen drive is a very compact version of the storage device, and it is also highly portable. So it is based on the same technology as the solid state disk, that is flash based semiconductor technology. And these are the different examples of persistent storage devices that we use in our computer system. So now let us see how the operating system manages these storage devices. So before we start talking about how the operating system manages these storage devices, let us first of all understand this hardware interface that is exposed by the storage device to the operating system. So let's quickly see how the storage devices appear from the perspective of the operating system. So this is a figure that I have taken from the previous video. So let us see what is the hardware interface that is exposed by the storage devices to the operating system. So the first point to note here is that the storage devices come in the form of an IO device. And as we know, any IO device has two parts. First, there is the device itself, and then there is the device controller that is associated with the device and is responsible for controlling the device. So I have assumed a hypothetical computer system which has three storage devices, that is the disk, then there is the USB, and then we have a CD-ROM. And associated with each of these devices, there is a specific device controller, right? And this is how the interface looks like from the operating system's point of view. So each of these storage devices exposes the interface that it is a sequence of blocks, and each of these blocks has a unique address. And in order to read or write data from these devices, you have to specify the block addresses from where you want to read the data, right? Read or write the data. And as you can see, each of these devices has a different block structure. The number of blocks, the size of the blocks, and internally the block structure is different for all of these devices. So this is the view for the disk, this is for the USB, and this is for the CD-ROM. So here I just assume a hypothetical example to give you a basic idea. And the major point here is that all of these block structures are different because these are different storage devices. They internally will be implemented in a different way. They will have different working mechanisms, and not only that, they will also be manufactured by different companies. So it is very possible that all of these will have a different block interface. So now let us see what the operating system does to simplify this block interface. So as we also discussed in the previous video, this device controller interface, or the hardware interface where each of these devices have a unique interface, this is very difficult to deal with because as you can see, all of these storage devices have the same purpose, that is to store data persistently. But now for doing the same thing, let's say you want to write a code to read or write blocks from these devices. For doing the same thing, you'll have to deal with three different interfaces. Hence, you'll have to write three different pieces of code. And this is very non-intuitive and counterproductive as a software developer. So we also saw what the operating system does to simplify this problem is that it defines a device neutral, or we can say device independent interface. This is a uniform interface which all of the storage devices in the system have to follow. And the way this is done is by having a piece of software which is called the device driver. The device driver bridges the gap between these device specific interfaces and this uniform device neutral interface. So just like for every piece of device, we had a piece of hardware like the device controller. In the same manner, we have a piece of software that is the device driver associated with each of the devices. And its responsibility is to bridge the gap between the individual device specific interfaces and this uniform interface. And as you can also see at this uniform interface, the block structure is also very uniform. It's not like this where every device has their own block structure. The size of the blocks, the internal block structure that has been defined by the operating system is also very uniform. So as you can see, with the help of the device drivers, the interface of the storage devices that is exposed to the rest of the operating systems is this uniform interface, and the rest of the operating system will build on top of this uniform interface. So as you can see from the perspective of the operating system, after the device drivers have simplified the interface, this is how it looks like. It's a uniform sequence of blocks where each block has a unique address, and now the operating system has to work with these blocks and further simplify this interface. So now let us talk about how the operating system manages the storage devices. So we are going to look at both the fundamental responsibilities that the operating system has to play in the context of each piece of hardware device. The first one is to make sure that the hardware is easy to use, and that the operating system ensures by providing an abstraction, which is kind of a virtual resource that it builds on top of the actual physical resource. This virtual resource is much more easy and powerful to use. And then the second fundamental responsibility of the operating system in the context of any piece of hardware is to make sure that it is used in an efficient manner. and that the operating system accomplishes by doing a careful resource management. So now let's talk about how the operating system manages the storage and makes it easy to use. So we had started our discussion at this device controller interface level, and we saw that the problem with this interface is that all of the devices have a unique interface, right? And that is why this block structure is different for all the devices. So there is non-uniformity at this level. Then we saw that the device drivers solve this problem by providing a uniform interface for all the storage devices. So they bridge the gap between these individual device specific interface and this device neutral or device independent interface. So now the rest of the operating system works with this consistent and uniform view of the storage devices. At this level, there is no discrepancy between the different blocks of different storage devices. But even this level has its own complexities. So now the problem with this level is that as a user, if you have to read or write data from these blocks, then you have to deal with block addresses, right? So let's say there is some data on your storage devices, and first of all, if you want to store the data, you'll have to provide the exact block addresses where you want to store that data. And when you have to read that data back, you have to remember where you had stored your data. You have to provide those block addresses again, right? So you see, dealing with these block addresses has its own challenge, and we don't want to get messed around in these block addresses. So what the operating system does, it provides an abstraction that makes it very easy to use these storage devices. So what is that abstraction? It is called a file. So the file is basically a logical unit of persistent storage. It's the smallest unit of persistent storage, you can say. And any data that you want to store persistently, you can put that into a file, give it a name, and the operating system will then take care of the rest. So as you can see here, we have three different files. One is a text file, one is an image, and finally we have a video file. So as you can see, files support different variety of data formats, and all of the related data has been put into one single logical unit. So this video file is one related unit of data. Similarly, this image is another related chunk of data. So now instead of dealing with these block addresses, these files are mapped to the blocks by the operating system. So you can see this is the text file. It is mapped on the disk from 1 to 4. This is the image. It is mapped on the USB device. And this is the video file that is again mapped to the disk. So now you don't have to provide these block addresses. You as a user can just provide the full path to the file, that is a English readable text. And once you provide the path or the name of the file, the operating system figures out where the file was stored, what are the block addresses for that file, and now you can easily read or write your data. So this is how the abstraction of persistent storage looks like. It's a file, and it makes the usage of storage devices very easy to the user. So this is how the complete picture looks like. As you can see here, we have the storage device, and at the operating systems level, the view is that the storage device is a sequence of blocks, but the user does not have to deal with these blocks, right? They have this abstraction of a file. So the operating system creates this abstraction over these sequence of blocks, and now the user, whenever they think of the persistent storage, they think in terms of files. So what the user will do, they will group all of their related data and put it into one single file. It's a logical unit, and give it a name. And that is how it becomes easy to handle with their data, right? So now the operating system's responsibility is to map the data in these files to the individual blocks on the storage device, right? So now the user does not have to deal with the block addresses. They can just provide the name of the file, the path of the file, and they will have the data. Another very important point that we did not talk about is that the view that is given to the user is that the data in the file is arranged in a continuous fashion. But in reality, the data could be all scattered in the persistent storage. So as you can see, let's take the example of this text file. It has 4 blocks. It is not necessary that all of these blocks be arranged continuously. They can be scattered all across the disk. But even in that case, the view that will be provided to the user is that the data in this file is continuous in nature. So this is very similar to the example of the virtual memory we saw in the previous video, right? So there, even if the data is all scattered on the physical memory, the view that is provided to the process or the programmer is that memory is continuous in nature. So that was possible because the addresses in the virtual address space were continuous. So even if the data was all like arranged in a non-continuous or scattered manner, the view of the memory remained continuous for the process or the programmer. In the same way, this is how in the same way it works for the case of files also. The addresses in this file will be continuous, and they can be mapped or arranged in a all scattered manner. The view to the user remains that the data in the file is arranged continuously. So this is how it becomes very easy to use the storage devices for the user. Another important point about the files is that here the view to the different processes that the operating system is trying to provide is that the storage device is a shared entity, right? But in the case of other abstractions, let's take the example of the CPU. There the operating system was trying to provide the illusion that every process has a private CPU. In the same way, by providing different address spaces, the operating system was creating the illusion that the memory is private to each of the processes. But in the case of storage devices, when you talk about files, any process can access these files and the storage devices if they have access to it. So this is one of the fundamental differences between how the operating system manages the storage device versus the CPU and the memory. In that case, it was trying to create an illusion that that particular resource, that is the CPU or the memory, is private to the process. But in this case, in the case of storage devices, that is not the case. The storage devices are shared resource, and all the processes can access the files on the storage device. Another important point is that any file has several associated attributes as well as operations. So what are these file attributes? So there are several pieces of information associated with a file, and those are called file attributes. So these pieces of information tell a lot of things about the file. So let us see some examples. So this is from the Windows operating system. So first of all, any file will have a name, and apart from the name, there is an extension. So the name is given by the user to identify the file, right? So now that we don't deal with block addresses, we have to provide another or alternate way to identify the file. And for that, we have a file name. And another thing is that the extension, the file extension basically denotes the type of the file. So there are different types of files that are supported on the system. There could be a text file, there could be an image, or there could be a video file. So all of these different file formats have a different extension, and that extension is basically to determine what is the type of the file. So in the case of an image, this is a .png file, right? And then if you open the file properties in Windows, then you can see all of these attributes. So here you have the name of the file, then the type of the file. Another extension for image files is the JPEG file. Then it says opens with, basically which is the application or the default application that will be used to open this file. That is also a file attribute. Then this is the location. So the location is the full path to exactly where the file is located. So in the next slides, we'll talk about directories and how these file paths are created. But basically the thing is, this gives you an idea where exactly in the storage device this file is located. Then this is the size of the file, the total amount of space that the file is occupying on the disk, right? So this was about the size. Then there are several dates. This is the date of creation. This was the date of last modification, and this was the date of last access. So these are all important pieces of information that are associated with each file. And then some of the attributes are the security and permissions. You can also make files hidden. So these are all the different properties or attributes that are associated with a file, and they tell a lot about the file that we are talking about. Now let us talk about the operations. Apart from the attributes, another important thing that is associated with the file is the file operations. So operations are basically actions that you can perform on any file. And here I have listed a few of the examples in the sequence of the events that happen in the lifetime of a file. So basically the first thing that you will do is create a file. When you create a file, you reserve some space on the persistent storage where you will be putting your data. You give it a name, a proper extension, and that is how a file is created. And now it is ready to use. You can put your data into the file. Before you can use the file, you have to open the file. So you can open the file by double clicking on the icon, or you can also open any file by programmatically or opening it via the code. You just have to provide the location or the name of the file, and then it is ready for reading or writing. So when you open a file, since you have just created it will not have any data initially. So first of all, you have to write some data onto the file. So when you put some data into the file, that is how it has some contents. That is what is stored on the persistent storage. And after you have written some data, now you can fetch that data. So this is where the read operation comes in. So you can read whatever data is present in the file by specifying the exact address from which you want to read. So when I say address, I do not mean the block address. I mean within the file, the offset from where you want to read the data. And once your usage of the file is done, you can close the file, right? All of the changes that you made to the file, that will be properly saved to the persistent storage. And finally, when you don't have any further use of the file, you are done with using the file, you can then go ahead and delete that file. Once you delete that file, the data that is present on the persistent storage, all of that will be removed, and that space will be freed up for any other file that you can store. So these are the operations that are associated with the file. So once you have an idea of the file attributes and the file operations, you have a good idea of what is a file. It's an abstraction that is created over the persistent storage, so that we don't have to deal with the blocks, and you can put all of your related data into one logical unit. It has several pieces of information which is called file attributes, and if you want to do any action or manipulate the file, then you have different operations that are there associated with the file. So you can see how this abstraction of a file makes it very easy for us to use this storage devices. So till now we have assumed that files are only used to store data on the storage devices persistently, but they have other important use cases also in the operating system. So a very important use case specifically in the Linux operating system is that the files are used to model the IO devices. So in the Unix based operating system, all of the IO devices are treated as files. So let us see how. So let's take the example of the keyboard. So the keyboard is designated the standard input device, and in the same way the display is treated as the standard output device. And for each of these devices we have special files that is called standard input for the keyboard, and for the display we have the standard output and standard error files. So whatever characters that the user types are put into this standard input file, and any process who wants to read the characters of the keyboard can read those from this standard input file. So you see how the standard input file models this keyboard. In the same way, whatever output has to be sent to the display, that is put into these files, standard output and standard error. So this is used for displaying the normal output, and this is used for error logging. So these two files are used to model the display in the Unix based operating systems. So whatever data that the process will write to these files will then be displayed to the monitor. So this is how the IO devices, all IO devices are modeled as files on the Unix based operating systems. So the files are not just used for storing the data persistently, they can also have other important use cases, as you saw, that is to model the IO devices. So when it comes to managing the storage devices, then files are not the only abstraction that the operating system provides. There is another abstraction that is called the directory, which is provided by the operating system. So now let us understand what is a directory and why do we need it, and how does it make using the storage devices easy for us as a user. So in order to understand why do we need directories, let us understand with an example. So the point is that as a user, we will have several different files while using the computer system. So here I have an example from my own work only. So let's see some of the example types of files that I have when I'm doing this work of shooting these videos. So I start my work with reading some books. So I will have some PDF of books. Then after reading those books, I prepare some notes in a text document. And once the notes are ready, then I convert them into some slides, right? I make slides on different topics, right? And once the slides are ready, then I record the shoot the videos, and that is how the tutorial videos I make. And since all of these I am doing for my YouTube channel, there are some other files also that is associated with my channel, like the logo of the channel, the banner of the channel. So this is an example of the different range of files that I deal with while doing my work. And again, this is just a hypothetical example. In reality, the number of files that I deal with becomes very large at times. So the point is that as a user, we'll have different files, many files, and there is a need to organize these files in some way, because otherwise there is a whole bunch of files and it will be very difficult to keep track of all these files. So let us see how the directories help us to manage and organize these files. So now let us see with an example how we can use the directories to organize our files. So I have taken the same set of files, the same example that I discussed in the previous slide. So these gray boxes that you see, these are the files that we just saw. And these red rectangular boxes, they represent the directories. So as you can see, what I have done, this picture is very easy to understand. What I have done, I have clubbed the related files into one directory, and I have done this in several places. So the images folder, so the folder is another name for directories, and we can use directories and folders interchangeably. So basically this is the images folder, and all of the images that were there related to the YouTube channel, the logo and the banner, I have put them in the images folder, right? And similarly, all the video files that were there, they have been put in one directory, that is the videos directory. So apart from the images folder and the videos folder, the remaining files that were there, in a way they were some kind of documents. It could be a text document or a PDF document or some slides, but all of them were documents. So I have put them in the documents folder, and I have also clubbed the slides together into the slides directory, because they are somewhat special and different from the text documents and the PDF documents. So as you can see, a directory can not only contain file, but it can also contain other directories. So document contains these text files, these PDF files, and apart from that, it also contains the slides directory. And finally, since all of these directories, that is the images, documents and videos, contains files that are related to my work, so I have grouped all of these directories into one single directory, that is the work directory. So this is how one could group their files and organize them. So now we understand how we can use the concept of directories to organize our files. But let's now try to understand how these directories are internally implemented inside the operating system. So within the operating system, the directories are implemented as files. So basically, the directories are just special type of files that are used to group the other files. So implementation wise, there is not a very drastic difference between the directories and the files. The directories built on top of the files. So this figure that you see is another representation of the grouping that we did in this case, right? So this figure is just another way to represent that. So as you can see, both the directories and the files, I have tried to show them in a similar manner. It's just that these files, the files that are colored in red color, they are directories, and they are special type of files that have been used to group these normal files, right? So this is how the operating system provides the abstraction of the file, and a directory is just a special type of file. So it's another abstraction that builds on the file, and using files and directories, the operating system makes the usage of storage devices very easy for the user. So the next point is that just like in the case of files, for directories also we have a set of attributes. Basically, there are several pieces of information associated with a directory, just as in the case of file, and they are called the attributes. Since directory is a special type of file, this is quite obvious. And apart from the attributes, we also have a set of operations, right? So as you can see, these are the attributes that are related to a directory. I have taken the example from the Windows operating system. So first of all, there will be a name associated with each directory that we can use to identify that. Then as you can see, there is a type. The type is file folder. So this identifies that this particular file is a special type of file and it's a directory. Then again, just like a file, we have the location, the size, that is the space that particular directory occupies on the disk. Then it also contains another information, that is how many files it contains, and not just files. A directory can further contain more directories or folders, so it contains information about that also. Then there is the date of creation, and finally some other attributes also. So this is how there are several pieces of information that is associated with a directory, just like we had in the case of files, and these are called the attributes. And apart from the attributes, we have certain operations. So these are operations that can be used to manipulate the directories. This is very similar to how it was in the case of the files. So let us go over these operations in a brief way. So first of all, it starts by the first operation that you will do. You'll have to create a directory. So directory is a special file. You have to create that file. and then you can open that directory to put more files into that. So that is how before using that directory you have to open it. And just like in the case of the files, you can open it both in a programmatic way, that is via code, or you can double click on the icon of the directory and open it. And once you have the directory created and opened, then you can write some data into it. So when we say we have to write some data, we mean that we can group some files and put that into this directory. So the contents of a directory will be other files or other directories, right? And when we have written some data into this directory, we can read that, we can fetch the contents of the directory, we can see what are all the files or folders that are part of this directory. Then once the usage is done, we can close this directory, and when we don't need the directory, we can delete it, which will free up the space that the directory occupies on the disk. So this is how there are several attributes as well as operations associated with a directory, just like a file. So this gives you a much more better idea of what is a directory and how it is used. The next point about the directories is that they introduced a notion of hierarchy within the files. So when we did not have any directories, then there was just a collection of files, there was a flat structure. But when you introduce the directories, then there is this tree like structure, right? And there are different levels. At the very top there is this work directory. Then at the second levels there is a categorization depending on the different types of files. So there are images, then we have documents, then we have videos, right? And within the documents folder also, as you can see, there is another categorization based on whether there are slides or not, right? So the slides folder contains the slides and the rest of the files are outside this folder. So you see how the directories introduced a notion of hierarchy. There are different levels of categorization, and this leads to a structure or organization within the files. So the final point talks about how we can refer to the individual files and directories with a unique name. And for that, we have the concept of path names. So what is a path? So basically, as you can see, these files and directories have been organized in a tree-like structure, a hierarchical structure. And in order to get the path of any particular file or directory, you have to start from the very top level and start traversing this tree, and the file or directory, the entities that you encounter while traversing the tree in order to reach that particular file or directory, those entities together make the file path. So let's take some examples. Here the first example is of this banner.jpg file. So in order to reach this file, you have to start with the top level directory, that is the work directory. Then you have to go into the images directory, and there inside this directory resides this banner file. So as you can see that this path name consists of all those entities that we encountered while traversing to this banner file, and they have been separated by a forward slash. So this is a delimiter that is used to separate the different entities. We can use some other delimiter also. Some operating system use the forward slash and some use the backward slash. So it is, the full path name is slash work slash images and finally slash the banner.jpg. And in a similar way, let's take another example. Here you can see the path name for slide1.ppt. So if you see, you have to start traversing from the work, then you go into the documents folder, then inside the documents you go into the slides folder, and finally you reach the slide1.ppt. And that is how all of these four entities, if you combine them along with the forward slash, then you get the full path name. So this is how the concept of path names work. So within this hierarchical structure, you have to traverse from the top of the tree, and all the nodes that you encounter while traversing to that particular file or directory, all those entities, if you combine them along with the delimiter, then you get the full path name, and then you can uniquely identify any particular file or directory within this set of files. So we have seen how the operating system provides the abstraction of files and directories to make the storage devices easy to use. So we started with this level, that is the device controller interface level, where we had non-uniform blocks. Then we saw this device independent layer. Here we are still dealing with blocks, but they were uniform. And finally, the operating system implements the abstraction of files and directories over this block structure to make it easy for the users to use the persistent storage. And the portion of the operating system that deals with this files and directories, that is responsible for managing the persistent storage, is called the file system. So when we talk about the files and directories in the upcoming videos in future modules, then we'll see the file system in more detail. So we have understood what is the file system. It's the portion of the operating system that manages these files and directories, right? And we are familiar with the file system actually. The user interface exposes this file system in the form of a file explorer. So let's quickly see this. So within the Windows operating system, this application that you see, this is a file explorer, and you can think of this as the front end of the file system. This gives you the information about the different drives that you have. Then you can see all the files and directories that you have in your computer. So this is this file explorer that you see. You must have all used this file explorer. This is the front end of the file system. In the back end, you can think of the operating system internally will be implementing these files and folders, and on top of that, this file explorer gives you a view of the different files and directories that are there in your computer system. So now we have seen how the operating system fulfills its first fundamental responsibility in the context of the storage devices, that is making the storage devices easy to use. So as we have seen, it provides the abstraction of files and directories over the persistent storage. So these are virtual resources, and whenever the user has to use the persistent storage, now they will think in terms of files and directories. So after seeing how the operating system fulfills the first responsibility, let us now focus on the second responsibility, that is how does the operating system ensure that the persistent storage is used in an efficient manner. Let us see what are all the things that the operating system undertakes while doing the resource management for the persistent storage. So let's see how the operating system manages the storage and ensures that it is used in an efficient manner. So now let us talk about how the operating system manages the persistent storage devices so that all the user applications in the system can use this hardware resource. So basically, as you can see, there are several user applications in the computer system, and when they will be processing, they will generate some output data, and that data that has been generated after processing cannot be left in the primary memory because the primary memory is volatile in nature, and when the system is shut down, all of that data will be lost. So in order to keep that data so that we can retrieve it at a later point in time, they have to be written somewhere safely in a persistent fashion. So that is why all of these user applications have the need to store their data persistently on these storage devices. Hence, the operating system must ensure that it carefully does a resource allocation, right? It manages them in an efficient manner so that the requests that come from the user applications for storing their data persistently can be properly fulfilled. So let us now see what are all the things that the operating system has to do or keep in mind while doing a resource allocation of these storage devices. So the first thing is that at the level of the operating system, these storage devices are a sequence of blocks. So the very first thing is that whenever there is a new file created or a directory created, then the operating system has to figure out the blocks in which the data of that file or directory will be stored. So file allocation means finding out the blocks and mapping the data of the files to those blocks. So as you can see here, this text file, that is this sa.txt, is mapped to the disk from 1 to 4. So first of all, the operating system has to figure out these blocks. Then only after ensuring that these blocks are free, then only the operating system can map the data of these files on these blocks, right? As you can see, there are several different files allocated at different blocks. So file allocation is a very important responsibility for the operating system. Another very important responsibility of the operating system is to manage the free space. So as you can see on this storage device, this pink region, this is currently free, that is, it does not store any data, and these gray regions are currently allocated. Some file or directory is stored on these blocks. So managing these free blocks, keeping track of the free blocks is the responsibility of the operating system, because whenever any new file or directory will be created, then it has to search among these free blocks and allocate some of them for the new file or directory, right? So the free space management is another responsibility that the operating system has to take care of when it comes to doing the resource allocation for these storage devices. Some other aspects that are related to the efficient usage of these storage devices is the performance. So basically, reading or writing from these storage devices is a slow operation. So the operating system uses certain techniques that speeds up the reads and writes. So for speeding up the reads, basically there is a technique called caching. So what the operating system does is that there are certain blocks which are more popular or which are more frequently accessed as compared to some other blocks. So these popular blocks, the operating system reads into the memory. Basically, it caches them into the memory. And whenever some process has to now access this data, then it can be directly like fetched from the memory instead of going and reading from the disk, right? So this is how, by caching certain popular blocks, the operating system can speed up the reads for the storage devices. And when it comes to speeding up the write operations for these storage devices, there is a technique called buffering. So the idea is that a large write operation is much more faster than several small write operations. So what the operating system does is that it clubs together several small write operations and like merges them into one big write operation. So that big write operation will be much more faster compared to the several small ones. So this is how the operating system buffers the small writes. This is the idea behind buffering. This speeds up the write operations for the disk or the storage device. Basically, for speeding up the read operation, there is the caching, and for speeding up the write operation, there is this technique of buffering. There are several other things that the operating system does while managing these storage devices. I'll not go into the details of all of them, but just mention them in brief. So the operating system has to ensure that the data that is being written to the disk is written in a reliable fashion, because if there is any system crash, then in that case that data has to be written reliably, because anyway we are not relying on the primary memory, we are relying on the persistent storage. So reliability is one thing that the operating system has to take care of, right? And apart from reliability, there are things such as storage initialization. So when you buy any storage device, at that time it is not formatted. So it has to be first of all formatted and partitioned into different drives. So in Windows, when you see C drive, D drive, all of that have to be created. So formatting is another thing, that is storage initialization is another thing that the operating system takes care of, right? So we have seen the different things that the operating system does to fulfill its second fundamental responsibility, that is to make sure that the storage devices are used in an efficient fashion. So there are several things that the operating system does when managing the storage devices. We talked about the resource allocation, that is allocating the storage blocks to the files. Then there is free space management. And when it comes to performance, then operating system uses techniques like caching and buffering to increase the performance of the storage. And apart from these, it also takes care of certain miscellaneous activities like storage initialization, formatting, and ensuring that the data is written in a reliable manner. So all of these are the responsibilities of the operating system, and it does a careful resource management in the context of storage devices so that they are used in an efficient fashion. So guys, this was it for this video. In this video, we studied how the operating system manages the storage devices and makes them easy to use by providing the abstraction of files and directories, and undertakes several different responsibilities when it comes to managing the resource to ensure that the storage devices are used in an efficient fashion. So this was it for this video. Thank you very much for watching, and I will see you in the next video. Thank you.